distributor feed at the center. In this type of feeding, the center of the distributor is connected to the supply mains as shown in figure. It is equivalent to two single feed distributors, each distributor having a common feeding point on length equal to half of the total length. The distributor is here nothing but AB, where the main feeder is point at point C, which is located just middle of the distributor. On this portion current I1, this portion current I1 plus I2, this is I2, 3 plus I4, this is I4. This point is I1 current, this is I2 current, this is I3 current, this one is your I4 current. So at point C, the given is middle of the distributors. Uniformly loaded distributor feed at one end. Figure shows the single line diagram of a two-wire DC distributor. AB feed at one end A and loaded uniformly with I ampere per meter length. It means that at every 1 millimeter length of the distributor, the load tapped is I ampere per meter. Let L meter be the length of the distributor and R ohm be the resistance per meter turns. This one is the distributor which will be fed at one end. This is fed at this other end. Length is supposed to be L. The load points are I represented here. So now consider a point C on the distributor at a distance x meter from the feeding point A as shown in figure. Then current at the point C is equal to I into L minus I into x ampere, that is equal to I common L minus x ampere. Now consider a small length dx near point C. Its resistance is R dx and the voltage drop over length dx is V is equal to I whole into I minus x R dx, that is equal to I whole into R, I R whole into L minus x dx. Total voltage drop in the distributor up to point C each is equal to I into L minus I into x ampere, that is equal to I whole into L minus x ampere. Now consider a small length dx near point C. Its resistance is R dx and the voltage drop over the length dx is dV, that is equal to I whole into L minus x R dx, that is equal to I R whole into L minus x into dx. Total voltage drop in the distributor up to point C is V is equal to integration limit 0 to x IR L minus x dx, that is equal to IR common Lx minus x square by 2. The voltage drop due to up to point B, that is over the whole distributor, can be obtained by putting x is equal to L in the above expressions. The voltage drop over the distributor AB, where I into L is equal to L, the total current entering at point A, R into L is equal to R, total resistance of the distributor. Thus, in a uniformly loaded distributor fed at one end, the total voltage drop is equal to that produced by the whole of the load, assumed to be concentrated at the middle point. AC distribution systems. Nowadays, electrical energy is generated, transmitted and distributed in the form of alternating current. One important reason for the widespread use of alternating current in preference to direct current is the fact that alternating voltage can be conveniently changed in magnitude by means of a transformer. Transformer has made it possible to transmit AC power at a high voltage and utilize it at a safe potential. High transmission and distribution voltage have greatly reduced the current in the conductors and the resulting line losses. The AC distribution system is classified into first is primary distribution system, second one is secondary distribution systems. So come to the first primary distribution systems. It is that part of AC distribution system which operates at voltages somewhat higher than general utilization and handles large blocks of electrical energy than the average low voltage consumer uses. The voltage used for primary distribution depends upon the amount of power to be conveyed and the distance of the substation required to be fit. The most commonly used primary distribution voltages are 11 kV, 6.6 kV and 3.3 kV. Due to the economic considerations, primary distribution is carried out by three-phase three-wire system. Figure shows a typical primary distribution system. Electric power from the generating station is transmitted at high voltage to the substation located in or near the city. This one is the distribution system. This is the 11 kV bus bar. Here 3-phase wire is there and substation, that is 33 by 11 kV substation is there, through which 11 kV supply will be generated, and some part goes to the big consumer factory which requires 11 kV 3-phase, and our substation also giving 3-phase 11 kV supply. Another substation is there, that is 11 kV supply is given. Then this one is your primary distribution systems. Secondary distribution system. It is that part of basic distribution system. The secondary distribution employs 400 to 230 volt 3-phase 4-wire system. Figure shows a typical secondary distribution system. The primary distribution circuit delivers power to various substations called distribution substations. The substations are situated near the consumer localities and contain step-down transformers. At each distribution substations, the voltage is stepped down to 400 volt and power delivered by 3-phase 4-wire AC systems. The voltage between any two phases is 400 volt and between any two phase and neutral is 230 volt. The single phase domestic loads are connected between any one phase and neutral, where as 3-phase 400 volt motor loads are connected across 3-phase line directly. This one is distribution systems. This one is 11 kV 3-phase line. The primary side is delta connected and secondary side transformer is star connected. This is a 11 by 0.4 kV transformers. These R phase, Y phase, B phase are clearly indicated. This one is neutral line, and the houses are given single phase supply. Some phase neutral with R phase, another house neutral with Y phase, another house neutral with R phases, and the factory requires R, Y, B along with your neutral lines. So here the phase to phase voltage, that is 400 volt. This is R to Y phase is 400 volt, B to Y voltage 400 volt, but here neutral to R phase is 230 volt, neutral to Y phase is 230 volt, neutral to B phase is 230 volts. AC distribution calculations. AC distribution calculations differ from the house of DC distribution in the following respects. First bit, in case of DC systems, the voltage drop is due to resistance alone. However, in AC system, the voltage drop are due to combined effect of resistance, inductance and capacitance. Second, in DC system, addition and subtractions of current and voltage are done arithmetically, but in case of AC system, these operations are done vectorially. In an AC system, the power factor has to be taken into account. Loads tapped off from the distributor are generally at different power factors. There are two ways of referring power factor, that is, it may be referred to supply or receiving end voltage, which is regarded as the reference factor. It may be referred to the voltage at the load point itself. There are several ways of solving AC distribution problems. However, symbolic notation method has been found to be most convenient for this purpose. In this method, the voltages, currents and impedances are expressed in complex notations, and the calculations are made exactly as in DC distribution system. Methods of solving AC distribution problems. In AC distribution calculations, power factors of various loads currents have to be considered, since current in different sections of the distributor will be the vector sum of load currents and not the arithmetic sum. The power factor of the load current may be given, that is, with respect to receiving or sending end voltage. With respect to load voltage, each case of shall be discussed separately. Power factor referred to receiving end voltage. Consider an AC distributor AB with concentrated loads of I1, I2 tapped at point C and B as shown in figure. Taking the receiving end voltage VB points are the reference vector. Let the points as the reference vector. Let lagging power factor at C and B be the cos phi 1 and cos phi 2 with respect to VB. Let R1 X1 and R2 X2 be the resistance and reactance of the sections AC and CB of the distributor. So this one is a distributor feed at single end point R1 plus JX1. This first load is at point C and second load at point B. The load is here I1 cos power factor cos phi 1. Load is here I2 power factor cos phi 2. So this impedance is R1 plus JX1 and this impedance is R2 plus JX2. Impedance of the section AC ZAC is equal to R1 plus JX1. Impedance of section CB R2 plus JX2. The current of I1 is equal to I1 cos phi 1 minus J sin phi 1. Load current at point B I2 is equal to I2 whole into cos phi 2 minus J sin phi 2. Current in section CB ICB is equal to I2 whole into I2 whole into cos phi 2 minus J sin phi 2. Current in section AC is equal to I1 plus I2. I1 cos phi 1 minus J7 plus I2 cos phi 2 J sin phi 2. Voltage drop in section CB VCB is equal to ICB ZCB. That is equal to I2 cos phi 2 minus J sin phi 2 whole into R2 plus JX2. Voltage drop in section AC VAC is equal to IAC into ZAC is equal to I1 plus I2 ZAC. So that is equal to I1 whole into cos phi 1 minus J sin phi 1 plus I2 cos phi 2 minus J sin 2 whole into R1 plus JX1. So sending end voltage VA is equal to VB plus VCB plus VAC. Sending end current IA is equal to I1 plus I2. So this is the vector representations of this load. This one is VB voltage and the current is supposed to be your I2 and here the drop is I2R2, here the drop is I2X2 and this one is Z line, this is your VC line and this is ISCX1, this one is VA voltage. So cos phi s is the voltage between ISC and VA and theta is the angle between VB and VA and phi 1 is the voltage between VB and IA and similarly this vector represents some things. The vector diagram of the AC distribution under this condition is shown in figure. Here the receiving end voltage VB is taken as the reference vector as power factor of the load are given with respect to VB. Therefore I1 I2 lags behind VB by phi 1 and phi 2 respectively. Second, power factor refer to the respective load voltage. Suppose the power factor of the loads in previous figure are referred to their respective load voltages. Then phi 1 is the phase angle between VC and I1 and phi 2 is the phase voltage angle between VB and I2. The vector diagram under this condition is shown in figure. This is VB voltage and drop is resistive of I2R2 and reactive drop I2X2. This one is Z line, this is VC, this is ISC into R1, ISC into X1, this line is your VA line, this is one. And alpha is the angle between VC and VB and phi 1 is the angle between VC and IA and phi 2 is the angle between VB and I2 and this is the resultant voltage current of I1 and I2, that is your ISC. So ISC current is dissolved in two components I2 and I1.